This time we're having a look at the case of very high Q factors. This is the case where you can get some of this resonant peaking. You can get a gain out of the circuit which is greater than 0 dBs. Once again, it's often interesting to be able to work out where the poles are in terms of the resonant frequency and the Q factor, preferably without having to solve a quadratic equation. And something quite interesting happens in this case. We can start with the standard form of the denominator in terms of the resonant frequency and the Q factor. And note that for the poles, those are the values of j omega for which this expression is equal to 0. So they are the solutions of this equation. It's a quadratic. We could write that P is equal to minus B 1 over q omega naught plus or minus the square root of b squared minus 4ac all over 2a. We've done this before, and after a bit of simplification, the result we get is that the poles are minus omega naught over 2q plus or minus the square root, well, omega naught over 2q times the square root of 1 minus 4q squared. When q is very large, we can now neglect the 1 in comparison with 4q squared and approximate this as minus omega naught over 2q plus or minus the square root of minus 4q squared times omega naught over 2q. The square root of minus 4q squared is j times 2q. So that would just give us minus omega naught over 2q plus or minus j times omega naught. But that's approximate. There is actually a rather neat and elegant way of writing the locations of the poles, which is exact. And you can derive that by thinking about where the poles are in terms of a polar representation. So, let's imagine we've got an Argand diagram. There's the real axis, this is the imaginary axis, and we want to know is where are these poles on the Argand diagram? Well, if q squared or 4q squared is much bigger than 1, then we can take this expression and write it as minus omega naught over 2q plus or minus j times omega naught over 2q times 4q squared minus 1. That is the real part. This is the imaginary part. So, one of our poles might be, say, at that location there. Its real part is going to be minus omega naught over 2q. And its imaginary part is going to be given by this expression here, omega naught over 2q times the square root of 4q squared minus 1. Right, what is the magnitude of this pole? The length from the origin. And that's just good old Pythagoras again. The magnitude of the pole is the square root of the real part squared, omega naught squared over 4q squared, plus the imaginary part squared, omega naught squared over 4q squared times 4q squared minus 1. Well, if I multiply out this bracket here, I'm going to get square root of omega naught squared over 4q squared here, plus omega naught squared minus omega naught squared over 4q squared. That term is going to cancel out with that term. This is just going to be the square root of omega naught squared. In other words, it's just omega naught, the resonant frequency. The magnitude of the poles is just the resonant frequency. What about this angle here? I called that angle theta. Well, cosine of theta would be omega naught over 2q divided by the hypotenuse, which we've just worked out is omega naught. So cosine of theta is 1 over 2q. Well, that tells us where the poles are, very simply, in terms of the resonant frequency and the Q factor. And we don't have to solve any quadratic equations. In terms of the amplitude response, as we've seen before, if you have a large value of Q, then we're going to get some gain around the resonant frequency. It's a little difficult to draw an approximation of the gain around the resonant frequency in these cases, but the low frequency approximation and the high frequency approximation just work exactly as before. They would meet at the resonant frequency, and the gain at the resonant frequency is just the Q factor itself, expressed in this case in dBs. So here, where we have a Q factor of 10, the gain in dBs at the resonant frequency would be 20 times log to the base of 10, which is just 20 dBs, which is what we're seeing here. What happens in terms of phase when you get these very high Q factors is that the phase remains at its low frequency value of 0 for much longer than it does with lower values of Q, and almost goes off a cliff edge, a very sharp change in phase from 0 to minus 180 around the resonant frequency itself. Now, if you remember this graphical model that we had of poles and zeros, where poles were like these tent poles and a canvas was draped over them, then you can understand what's happening with those resonant peaks, perhaps. The poles we have here are very close to the imaginary axis for large values of Q, which means the canvas is pulled up very high, quite close to the imaginary axis, at around the resonant frequency of the poles. Plotting what it looks like for a frequency moving up the imaginary axis, we get this peak here, which directly corresponds to the resonant frequency. And you may notice that the maximum magnitude will occur at this point here, which is actually slightly below the resonant frequency. But as the Q factor gets higher and higher, the position of the maximum value of gain approaches the resonant frequency, but it never exceeds it. So a quick summary of the 3 special cases we've seen so far. For very small values of Q, we can approximate the poles as being minus the resonant frequency divided by Q and minus the resonant frequency times Q. For the special case of Q equals 0.5, both poles are at minus the resonant frequency. And for the case of very large values of Q, we have this exact formula. We can express them in terms of a polar representation of where the poles are, with the magnitude of the poles being omega naught, and the angle here being the arc cosine of 1 over 2q. There's one more special case that I want to talk about, and that's the case where q equals 1 over the square root of 2. And for why that's interesting, please see the next video.